Today, we're talking about a silent destroyer. It's a force that can turn brilliant engineering into, well, basically dust. And it's not about some big, dramatic explosion. It's about the quiet, relentless chemistry of corrosion. Let's dive in.
I want to start with just one number, 3.8%. Now, what's that? Well, that's the slice of the entire gross world product that we lose to corrosion every single year.
To put that percentage into perspective, we're talking about a financial hit of over $2 trillion a year. This isn't just about replacing a rusty pipe here and there. No, this is a massive hidden tax on our global economy, and it affects everything from our infrastructure to global trade.
You know, when most of us hear the word corrosion, we immediately think of rust on an old car, right? But that's just one tiny part of the story. The real definition is much broader. It's any destructive and unintentional attack on a metal. Really, it's just nature at work. It's refined metals trying to get back to their more stable, natural state, like the ore they came from.
And this attack, it doesn't just happen in one way. Not at all. Corrosion is actually a whole family of different failure modes, and each one has its own unique way of causing damage. If you want to fight it, you've got to know your enemy.
So here are 8 of the most common types that engineers have to deal with. Now, we're not going to go through all of them, but you can see right away how complex this gets. You've got things like galvanic corrosion, which happens when 2 different metals are in contact. Then there's stress corrosion, where a part literally cracks under tension in the wrong environment. Each one needs a totally different game plan to prevent it.
Okay, let's start with the one we all recognize, uniform corrosion. Just like the name says, it's an even, predictable degradation right across the entire surface. And because it's so predictable, engineers can actually plan for it. They can just add a little extra material thickness, kind of like a built-in safety margin. But then you get something way, way more dangerous, pitting. This is a sneak attack. It creates these tiny little holes or pits. And it's so insidious because a part can look totally fine. It might have lost less than 1% of its total weight. But one deep pit, just one, can cause a sudden, catastrophic failure out of nowhere.
And this one? This is a perfect example of how the design itself can create the problem. Crevice corrosion is this super intense attack that happens in tiny, stagnant gaps. Think about the space under a bolt head, or between 2 plates, or underneath a gasket. The fluid in that tiny space gets trapped. Its chemistry changes, and it becomes really aggressive. The metal literally gets eaten away from the inside out. So what's causing all these different kinds of attacks? Well, it turns out that accelerated corrosion almost always boils down to the interplay of 3 key factors. And if you're an engineer or a designer, you absolutely have to understand how these 3 work together. All right, first up, the most fundamental factor of all, the material itself. I mean, what is the thing actually made of? The choice of metal or alloy you make right at the beginning sets the stage for everything else that happens. You see, a lot of so-called corrosion-resistant materials, like stainless steel, aren't magical. Their secret is something called a passive film. It's this microscopic, invisible layer of oxide that forms on the surface. And it's tough, and it even heals itself. It basically acts like a suit of armor, protecting the vulnerable metal underneath. But here's the thing. Not all armor is created equal. A standard stainless steel is great for a lot of things, but that passive film, it can be broken down by chlorides, think salt water. So for a really aggressive environment, you might need to step up to a high-performance alloy like Hastelloy. Its armor stays strong under much harsher conditions. If you choose the wrong material for the job, you're basically designing it to fail from day one.
Now for our second factor, the actual physical shape of the part. That's right, the geometry of a component can become its own worst enemy. And this is where you really start to see that classic conflict between designing something quickly to get it launched versus designing it for long-term durability. This quote from one of the sources just says it all. Every sharp corner, every little groove, every thread, it creates a point of high stress. These stress risers don't just make a part weaker mechanically, they can become the exact spots where corrosion gets a foothold and starts its attack.
Here's a perfect real-world example. In any piping system, it's almost never the long, straight runs that fail first. Nope, it's the elbows and the T's. Why? Because as the fluid turns that corner, it gets turbulent, and that turbulence can literally strip away that protective passive film, exposing fresh metal to be eaten away. A simple change in direction creates a corrosion hotspot.
And that brings us to the final piece of the puzzle, the environment it's all sitting in. This covers everything: the temperature, the pressure, and the specific chemistry that the component is exposed to day in and day out.
Now, here's something that might surprise you. The relationship between the environment and the corrosion rate isn't always a straight line. You'd think that more of a corrosive chemical would always mean more damage, right? But check this out. For some acids, the corrosion rate actually peaks at a medium concentration and then it drops off again. If you don't understand these kinds of nonlinear effects, you can make some really disastrous material choices.
So what are the biggest red flags to watch for in the environment? Well, temperature is a huge one. Hotter is almost always worse for corrosion. Chlorides, as we talked about, are notorious for attacking those passive films. High flow velocity can physically wear down the material. And even tiny things like little particles or bubbles in a fluid can act like a constant sandblasting, just accelerating the damage.
So there you have it. You've got these three factors: the material, the geometry, and the environment, and they're all working together. The big takeaway here is that you can't just react to corrosion after it starts. The only way to truly win this fight is to get way ahead of the problem.
And this, right here, is the most critical point of all. A coat of paint, maybe a special coating, that's a temporary fix. It's a bandage. The real battle against corrosion is won or lost in the design phase. It happens on the drawing board, long before any metal is ever cut.
So, how do we actually do that? Well, first, you design out those stress points. Use smooth curves instead of sharp corners. Second, you have to select your material for its actual service life, not just its upfront cost. Third, you design to get rid of those tiny gaps where crevice corrosion loves to hide. And finally, you have to truly understand and account for the real-world temperature and flow that your design is going to face.
And that really leaves us with a final question. With trillions of dollars and countless critical systems on the line, from bridges and pipelines to spacecraft, the real challenge is to shift our whole mindset. Are we designing for the short term just to get something out the door? Or are we really designing for true long-term durability against these quiet, relentless forces of chemistry?